heat transfer, the basic is the flow of heat, which is also known as thermal energy because it's an energy between objects. It always will go from the warmest one to the cold one. I remember when I was a little kid and I got the door of the fridge open, trying to decide what to have for dinner. And my mom always yelling like, close the door, you will get the cold will be out of the fridge. But actually it's the opposite because the outside air has a bigger temperature, so it will enter to the fridge. So the cold won't go away. So it's the opposite.
Welcome to another Refrigeration Mentor podcast. This is part 2 of a 2-part series with Gutner, with my good friends from there. And I'm excited for this conversation because refrigeration is all about heat transfer, mass transfer. And when we talk about energy, talk about refrigeration, it's all about transferring that heat. And I'm today with a product expert, heat transfer expert, Tania Herrera. She's a product engineer from Gutner. We met at a bunch of different shows and she continuously surprised me with the amount of knowledge she has on heat transfer. And today we're going to be diving into some of the fundamentals and basics of each heat transfer, why it's important to know as a technician, as a designer, as an engineer, because this is the fundamentals of refrigeration. We know we have evaporators and we have condensers and we have plate heat exchanger, but we really want to understand what affects heat transfer. And this is what we're going to be diving into today. Tania, welcome to the Refrigeration Mentor podcast. How you doing?
Hi, very happy to be here. Thank you very much for the invitation.
I'm so happy you're here because all the conversations we've been having at the previous events we've been seeing each other at is that you're really passionate about refrigeration. You really know your stuff and you spend a lot of years learning and developing your skills as an engineer. Why don't you talk a little bit about your background?
Yeah, sure. Well, I studied food engineering in Mexico City, which is very similar to chemical engineering, but focused in the food process. But I decided to be trained and to be expert in refrigeration side. So the last semester, I took a subject which was very related to refrigeration. And then I had the opportunity to enter to work in Gutner as an application engineer. So I was working in Mexico. I worked in Mexico for about almost 5 years, and I was very close with the factory and production. So that's very helpful in order to understand how everything works. And I recently moved to the US last year and with a new position as product engineer and key account.
Awesome. Yeah, that is wicked. And this is the journey of refrigeration, right? You start somewhere, you invest in yourself, and definitely a manufacturer like Gutner, there's so much to learn. I've been through some trainings and it's continuous learning with these manufacturers who are really developing and pushing the boundaries with the technology that you have. So last week in part 1, we hung out with your friend Will and we dove into controls on gas coolers. But now we're going to dive into heat transfer on gas coolers, which I'm super excited to talk about. Let's dive into some of the basics of what heat transfer is all about.
Yeah, sure. Let me start. I would like to share a presentation, but it's very basics. For the ones that can't see the screen, don't worry. It's just to make it easier to see, but you are not missing that much.
Yeah.
So let me share my screen and let me know when you can see it.
Yeah, I can see it.
Okay, so first it's the basics as we already mentioned. So for instance, what is heat transfer? So heat transfer, the basic, what I can see is the flow of heat, which is also known as thermal energy because it's an energy between objects. So it always will go from the warmest one to the cold one. So for instance, I remember when I was a little kid and I got the door of the fridge open, trying to decide what to have for dinner. And my mom always yelling like, close the door, you will get the cold will be out of the fridge. But actually it's the opposite because the outside air has a bigger temperature, so it will enter to the fridge. So the cold won't go away. So it's the opposite. But I will just keep going. So there are also 3 mechanism of heat transfer. So we have conduction, convection, and radiation. And for instance, the conduction is between solids because the heat is transferred through physical contact. So for example, when you hold a metal handle on a hot pot, the heat from the fire will eventually travel up to the handle and make it too hot to hold it with your hands.
Yeah.
So that's a conduction, just direct contact. And we also have convection, which is the heat transfer between gases and liquids. So the heat is transferred by the movement of the heated liquid or gas. This movement is caused by change its density as the fluid warms. So for instance, I also have this example of your daily life when you're heating a soup, for instance, that has many ingredients. If you collocate it in your oven, it will get warm, of course. But if you start to move it, it will be warmer sooner than later.
Yeah.
Sooner than if you don't do it. So that's an example of convection. There is two types, natural and forced convection. So the one that you are moving the soup is forced one because you are applying a force into it to make it faster. Natural will be if you just leave it that way to get it warmer. And lately we have radiation. So the heat is transferred through radiant energy, which is similar to light, like the sunlight that we received. If it's cold winter and we just want to get warm, we just stay outside and try to get some sunlight, right? So that's an example of radiation. And another example would be the microwave.
Yeah. Yeah, see, these are great examples, but all of these things can be a part of refrigeration, all these different types of heat transfers, conduction, convection, and even radiation type.
Yes, of course. As I'm going to mention more about it in the next slides. The application of refrigeration. And for instance, we also have different types of heat. So we have latent heat and sensible heat. And this is very important in heat exchangers and also in refrigeration. So sensible heat is literally the heat that can be felt. It's the energy moving from one system to another that changes the temperature rather than changing its phase. So this one can be measured with a thermometer. And for instance, we have refrigerants that doesn't have a phase change. So these ones work under the principle of sensible heat. For instance, when we have air coolers that will work with glycol, yep, we will have an inlet temperature and an outlet temperature. But the refrigerant will enter liquid and the outlet will be also liquid. Yep. So this is just a temperature difference. And we also have latent heat. And latent heat is the heat transfer required for an object to have a phase change without changing the body's temperature. So we also have refrigerants that works under this principle, which could be, for instance, ammonia or also CO2, that we have the evaporators. So that's why they are called evaporators, because the refrigerant will evaporate. It will enter liquid and the outlet will be gas, but the temperature won't remain constant, because on the evaporator we have latent heat and sensible heat. Well, if it's direct expansion, because we want a superheating at the outlet in order to make sure that the compressor won't have any liquid, and also to the thermostatic expansion valve work. So that's what we have to. Also in the condensers, for instance, we also have sensible heat, because we have the superheated vapor from the outlet of the compressor will enter to the condenser, and in order to condensate, first it needs to decrease its temperature until we reach the saturation point, and then it will start to condensate, to have a phase change from gas to liquid, but at a constant temperature.
I had such a hard time when I was first learning about refrigeration, about latent heat. Like, I understood sensible heat very well, but when I was first starting out, latent heat just didn't get to me. It didn't understand because I couldn't see it. You know, I could put my temperature probe on a pipe and then I could see the temperature change. I'm like, oh, the temperature is changing. But I could not visualize when I first started out inside that evaporator coil or the condenser, like an evaporator starting to boil off. And that's where latent heat is starting to happen. Did you have that when you first started to learn about thermodynamics?
Yes. Also, I mean, for instance, I also confused latent heat with sensible heat. Because I mean, sensible heat is the one that we have known all of our lives because we can measure it with a thermometer, right? But latent heat, yes. I mean, I didn't know an example of that. I just know that latent heat, it ends with T, so I can say constant temperature. So yes, it's that one.
Yeah.
But yes, until I was in college and we have an experiment with an evaporator with gas, then I realized that at the temperature it was constant, but it's something very difficult to see in real life. For an example, I mean, an example could be when you're boiling water, but you're not holding a thermometer in the boiling water, right? Because the vapor, it's hot.
Yeah.
It's 212 degrees in Fahrenheit.
Yeah. Yeah. No, and I love that. Okay, awesome.
So now that we have this is my favorite equation in the world, because this equation describes the performance of a heat exchanger. So every heat exchanger follows this equation. So its capacity equals the overall heat transfer coefficient that multiplies the heat transfer area, that also multiplies the LMTD, which is the main temperature difference between the fluids. On the following slides, I will talk about more in detail about them. And here we can see that it's a proportional relation or direct relation, which means that if I make one smaller, the capacity will decrease. And also if I make one of them bigger, the capacity will increase. But also in real life, sometimes it can happen that one of them was decreased. Like for instance, here I decrease the LMTD, so the capacity drops. And an example of this is when we have a condenser and the ambient temperature rises, because the LMTD in a condenser will be the difference between, the LMTD difference between the air and the condensation temperature. So if your ambient temperature increases, then your LMTD will decrease and you will have less capacity. So there are many options that not many options, but there are some options that you can do. And for instance, I know that in refrigeration, what we do is that we increase the refrigerant temperature, which means that we increase the discharge pressure and temperature in the compressor, right? In order to balance the decreasing of the LMTD. But also there are other options, like for instance, increasing the overall heat transfer coefficient. But I'm going to tell you how you can do that in the next slides, or what are the implications of doing that. So point by point. So for instance, the capacity, an example, is the heat load that the heat exchanger requires. So the required capacity is defined by the application needs, of course. In this case, I will talk about the cold rooms and also the condensers. So for instance, in the cold rooms, it's important to consider the product, the inlet temperature of the product, the outlet, the storage temperature of this product, the infiltration that you can have, the amount of product that you have, the heat produced by the motors, lining, persons that will be working there, etc. And for a condenser or a gas cooler, the heat load considers the heat absorbed in all of the evaporators of all of your installation, plus part of the heat generated in the compression process. So for instance, me as a heat exchanger manufacturer, I'm not involved in this part, but the contractors, that's their job to do all this calculus. So they only told me, like, I need this evaporator for 10 tons of refrigeration, or I need this gas cooler of 12 MVH of capacity. Yep. And here is the interesting one, because here is the overall heat transfer coefficient, and it's also influenced by the internal heat transfer coefficient and an external heat transfer coefficient. And what does this mean? So this means, for instance, that the internal heat transfer coefficient, or what happens here, also influence this term. So it refers to the refrigerant properties that we have here. Also, the velocity inside the tube, for instance, it's very important to have high velocity inside the tube in order to get a better heat transfer. It's like the same example. If we translate this into a daily example, it's the same as if you have your coffee and you wanted to drink it fast, you have to move it in order to get it colder, a little bit colder, because also drinking cold coffee is not good. But increasing the velocity, it increases its turbulence as well, and it increases the heat transfer. So this is good. But also it has a limit. Everything has a limit, because if we increase the velocity too much, it also increases the pressure drop, and it has an impact in the compressor, in the case of evaporators.
So I do have a question. So that's a good point, right? So now if a lot of new systems have capacity control, so they'll have a VFD drive on the compressor where we'll ramp up the mass flow and then slow the mass flow down of the compressor. So this will actually change that velocity in these coils as well as change the heat transfer?
Well, yes, because I think that everything is connected. So what happens in one item, it will impact the other one.
Yeah. So it's something really good to understand, because when you go into, and I've been doing a lot of compressor training lately. So you go in and you change the mass flow, you would see the heat transfer of the thermal heat transfer of that system. If you're doing a package system, you'll see that start to change. So the total heat of rejection. So as you start to change the capacity of that compressor, which is pretty cool to watch.
Yes, and something also important that I want to mention is that, for instance, we want also that the refrigerant covers the whole wall of the tube. So that's why we also need high velocities, because if the velocity is too low, then we will have a separation, because at the end of the day, we have a mixture of phases in the tubes, because we have a phase change. We have liquid and gas. So if there is no high velocity, the gas will go up and the liquid will go in the bottom, and then we will only have heat transfer in the bottom. Well, in the case of the evaporators, well, also in the gas coolers. But in the gas coolers would be the opposite.
Yeah.
Well, sorry, condensers.
Yeah, so and that makes sense. So you have, as that is flowing through a coil, just say if we're talking about a coil, so the copper pipe or stainless steel is going through, that takes into account all the surface area around the tube plus within the tube as it's going through?
Yes.
Yeah, awesome. Once again, it's hard to visualize that, you know what I mean? Because it's inside solid pipe and it's not clear, you don't look inside the pipe. But I've noticed over the years of me understanding and diving in more heat transfer, I look at the pressures and I see the temperatures, and I can actually understand what's happening inside that pipe. And that's where, okay, we know that this coil is full of liquid, or it's full of gas, or it's starting to condense at this point just through temperatures and pressures in the system.
Yes. So, well, I will show you a picture later that also will describe this better. That we want the liquid to surround all the wall of the piping.
I love that.
So that's on the internal heat transfer, and now we have the external heat transfer. So this one refers to the heat conductivity of the materials as well, because in this case, the fins is where almost the 90% of the heat transfer occurs. As well, it also refers to the second fluid. So in the fin, heat exchangers refers to the air. So, for instance, if we have higher, it's the same. Well, sorry, I'm going to start again. Yep. So this refers to the heat conductivity of the materials, and this is also depends of the application, of the needs of your application. For instance, if you have a condenser or a gas cooler that will be installed in a coast area, we strongly suggest you to consider fins with a quoting.
Yeah.
Because the saltness of the environment can cause corrosion in the aluminum fins, and you will have a short life in your heat exchanger. But if you consider a quoting, the heat conductivity of this fin will be less or will be smaller than the one that doesn't have a quoting. But I mean, it's something that we have to deal with, and we have to it's very important to consider.
Yeah.
Also, if we are talking about the evaporator, for instance, if we have smoking rooms, the chemicals that the industry use for this kind of applications are corrosive with some metals, and that's why we need to consider stainless steel or special coatings in order to avoid that. But the capacity, if we compare one heat exchanger with other coating, with coating and not coating, the one with coating will have less capacity than the other one.
Yeah, so in that case, I guess you would have to design it a little bigger. You'd have to have more surface area, for an example, with a coating one versus a non-coating one. But you need it. I've seen so many on the coast where it's just the tubes. There's nothing left because it just corroded all the fins off, and it's just the tubes pretty much left. So it's important to have that in certain areas, those corrosive areas. So that's great to know.
Yes, so this is something very important to take into account for the external or overall heat transfer coefficient, because it affects this part of the equation. And another thing that also takes part on this is the air, as we are talking about a thin heat exchanger, because we have a motor we have a motor that will pull air through the coil. So that's how we have the heat exchange, because it's between the air and the refrigerant inside of the piping, right? So also it will be good to have high velocities in the air, good turbulence in the air, and we make sure to have this with our fins, because the fins are not just plain metal sheets. They have some like corrugations that will increase the area and also will increase the turbulence of the air while passing through the coil. So this is also very important, but of course it also has its limitations, because more air will mean that you will need a bigger motor, and bigger motor will mean that you will have a higher power consumption, right? And the customer will be reflected that in their electricity bills.
Yeah.
But also, if we're talking about evaporators, if they are coolers, this means that we will have water, because there is humidity in the air, and your coil will be cold, right? Because you are cooling something. And when the air touches this colder temperature, the humidity in the air will condensate, and we will have water droplets inside of our heat exchanger. Well, within our heat exchanger. Yep. So if we have high velocity, these water droplets can go and blow out of the room, and we can have a problem with products. Or, well, you just don't want water. You just don't want raining inside your cold room, right?
And I've seen that many times before, where not because that necessarily sometimes is from defrost, and the defrost timer is not set right, or the drip time, and then on the roof it's all like, it looks like little droplets and drips because the fan's blowing that on there, or frozen droplets because there's an issue with the setup. But with different coils too, this will make heat transfer different. So there's larger coils and smaller coils. Some circuits you want to dehumidify that cold room more, and some you don't. So for example, a meat room, you don't want it to be pulling out all the moisture out of the meat right away. So you'd have more of a humid room versus a dehumidified room. I don't know if I said that right. One of the things that always got me, I didn't really understand, do you need a bigger coil to dehumidify or a smaller coil to dehumidify a room? Can you talk on a little bit on that?
Yeah, sure. Well, for instance, what we sometimes can do is that we have our evaporator with its cooling circuit, but also some customers ask us to have we call it reheat circuit, but it's for decrease the relative humidity on the room. So it can be also like within the same evaporator in the same unit. But if the load is too big, then we can have it separately. But usually you also don't want to have a big heat load in your cold room, right? And it doesn't operate like continuously 24/7. It's just short periods of time.
Yeah. And that's important to understand. So when you're sizing a unit, I know we're a little off topic here, but this is all about that heat transfer, because you're saying if we have a really wet evaporator, we got a lot of water on that coil, it's going to affect that heat transfer. Plus, we're going to blow that water on top of all the product. So we don't want that. And that will come into the sizing of that system, I'm assuming, and the temperature of the coil itself.
It depends on the airspeed. 2.8 meter per second is the maximum where the sputtering is starting.
Oh, thank you very much.
Yes, that's correct. Yes, we have some limits. So for instance, for freezers, we don't have the problem or the risk to take droplets out of the evaporator. So we can have very high velocities and it will be okay. But for cooler rooms, this is we have to be very careful with this. So as our colleague Bayrel, I hope I pronounce it correctly, mentions, we have some limits in order to avoid this kind of problems.
Yeah, no, and exactly. And these are the things that you need to understand about heat transfer and coils. Excellent. Let's keep going.
Okay, so now I'm going to talk about the heat transfer area. That it's, in this case, in our evaporators will be, as I mentioned before, the 90% of the heat transfer occurs in the fins. So if we want to increase the heat transfer area, we can always add more fins. But this means more materials, so it means that you will have a more expensive heat exchanger.
Exactly. Yeah.
But also there are limits, because if we're talking about evaporators, we cannot have many fins. We call it fins per inch, because then if we have evaporators, there is more likely to have ice formation in it. So we don't want our evaporator to be blocked with ice. So we also have some considerations when we have a freezer. We cannot go maximum that, for instance, 3.2 fins per inch. But if we have a cooler, then we can increase it. It depends on the room temperatures and the evaporation temperatures. But for instance, in the condensers or gas coolers, we can go for up to like 10 or 12 fins per inch. We have restrictions in some regulations, like for instance, in California, we have to comply to California Title 24. For instance, this one doesn't allow us to have more than 10 fins per inch in dry gas coolers. So this is something that we should also take into account. And also, the more fins you have, you will increase the air pressure drop of the air when passes through the coil, and that also has an impact on your fan. And remember that everything that impacts your fan will have an impact on the I just forgot the word.
Overload.
In the power consumption. Yes.
Yeah. And the cost too, right? The more you have to pull that through, then you get more power in that fan, and now you're increasing the power bill of your customer. So it all makes sense. And then this all comes back to heat transfer, which is super cool.
Yes. And now I'm going to, before I deeply enter to LMTD, I want to talk about something that is called parallel flow and counterflow, because this is also very important when designing a heat transfer. So a heat exchanger, sorry.
Yeah.
So this is an example of parallel and counterflow in a shell tube heat exchanger. So I found this more easy to explain rather than in another type of heat exchangers. But in a parallel flow, we both have the hot and the cold fluid flow in the same direction, entering at one end and exiting at the other end. So the temperature difference between these fluids decreases gradually along the length of the heat exchanger. So here we can see in this graphic, we can see how the temperature difference is getting smaller as it's still flowing. And in counterflow heat exchangers, the hot and the cold fluid flows in the opposite direction. So the fluids enters at the opposite ends of the exchanger. For example, the hot fluid enters at one end while the cold fluid enters at the other end. And here we can see that the LMTD is a little bit more constant while considering this. And for instance, this is something generally what I'm going to say, but it depends on the type of heat exchanger and also the refrigerant or fluid. But counterflow heat exchangers generally have higher efficiency because they maintain a larger temperature difference between the fluids throughout the heat exchanger.
Yeah, I've been seeing more and more, especially on CO2 systems. I see heat exchangers everywhere now in industrial applications. When would you see? When would you want to use a counterflow or a parallel flow? Like what applications? Why would I use a parallel flow? I know you said counterflow is could be more efficient or is more efficient in certain applications, but when would I use a parallel flow versus a counterflow? Can you talk about a couple of different applications for that?
Yeah, sure. Like for instance, when we consider sensible heat, so refrigerants that doesn't have a phase change, we have seen that counterflow is the one that is more efficient, as well as, for instance,
so that would be like a glycol system, I would say. For an example, I do a secondary system, glycol system in the supermarket that I work in. You would see a lot of that. That's exactly what it is, the counterflow. The parallel flow, I don't see too often, but I know I've seen it in a few applications.
But for instance, I have seen them in some of heat exchangers for ammonia, because I read a study and it said that due the physical properties of the ammonia, this is direct expansion. While direct expansion for this particular application, it was better to consider parallel flow. Because, for instance, they also have to consider the superheating circuit. Well, no, it's not a separate circuit, but we have to consider like the superheating part on your heat exchanger.
Yeah, so exactly. Super
that's
awesome.
why we found this.
Yeah, and for those who are just listening on the podcast, you can go and look this up very easily on Google, like parallel flow, and see a couple of different images on it. It's all over. It's easy to find that on heat exchangers. So yeah, thanks for sharing that.
Okay. So, for instance, what I mentioned, I mean, besides the parallel and counterflow, both of them have an impact on the LMTD, as we already see, right? And so here is the difference between the refrigerant and the air temperature. For instance, in evaporators will be the difference between the room temperature and the evaporation temperature. And if you want to make this bigger, for instance, I personally will never touch the room temperature because this one is defined by the application, which in refrigeration is mostly food. So if we already know that the storage temperature of this product is, I don't know, 34 degrees, it's better to stay it, because if we increase it, then we can have a quality problem. So what we can do, because I have seen many cases where we already have the evaporator and the customer says like, I know I can't pay more for this, but I need more capacity. And sometimes what it's only left is to decrease the evaporation temperature. But this, as mentioned before, has a direct impact on the compressor. So
So now you get that SST bigger, right? So now your compression ratio is getting bigger, more work on that. You are getting more work out of that evaporator because you're taking that SST, say, from a 25 degree Fahrenheit down to a 20 degree Fahrenheit SST to get a bigger TD. That's what you mean, right? To maintain the 34. Yep.
So it's never free. We can, I mean, we can get more capacity, but someone has to pay the price.
Yep. Yeah, that's totally fair.
And in the high side, we have the condensers or gas coolers or fluid coolers. If we have a refrigerant that doesn't have a phase change, the air temperature, the difference will be between the refrigerant and the ambient temperature. So there are some technologies that help us to decrease the LMTD in order to improve our heat exchanger. So for instance, the one that you can see here in the picture is a dry gas cooler, but sometimes we can add a spray system underneath that will spray water, and that will help us to decrease the ambient temperature before touching while touching the coil. Another one is the evaporative condensers because they work under the principle of wet bulb. So
And in CO2, we're
yes.
seeing a lot more of those adiabatic. I see tons of them out there, as well as those spray systems, atomizer, misting systems, to do that. And so really to keep those in those high ambient, dry locations, keep it below the transcritical point as long as possible.
Just that was something that I was going to mention. That also we have the adiabatic ones that also help us to decrease a little bit the ambient temperature, which will give us a bigger LMTD. So here are some advices to improve the heat exchange within your heat exchanger. Like for instance, as I mentioned before, we can always increase the refrigerant velocity or its turbulence. We have these that are called turbulators that sometimes we use, for instance, for refrigerants that doesn't have a phase change, like the oil coolers, and also indirect expansion evaporators. Or I mean, we can't fill all our heat exchanger with these turbulators because this also increases the pressure drop of the refrigerant.
So these would actually be, these would be actually in the tubes in certain locations because,
yes.
Okay, cool. I think I've seen that before, but it's coming back to me now. So that's cool. And so this here will just start to slow it down a bit. But like you said, if you put that in every pipe, that would have a massive pressure drop along your system. Yeah.
So I mean, it has its limits. Also, we can increase the passes. By increasing the passes in your heat exchanger, you will increase the refrigerant velocity. But of course, if you also increase too many passes, then you will have a high refrigerant pressure drop, and your compressor will pay for that.
Yeah, we'll pay heavily for that. Yes.
And actually, when you have a really high pressure drop, the performance doesn't improve. So it's in a very in a very like a space where we can increase the passes and we will have a better performance. We can also, I'm talking about velocity. We can also increase the air velocity, but as mentioned before, it has its limits. Talking about evaporators or talking about condensers, because we can have the water droplets carried out of the unit, or we can also have more power consumption in the case of condensers or gas coolers. And you will
just I want to add about counterflow and parallel flow. Parallel flow is suitable also for evaporators fluided, for ammonia fluided evaporators. Can be used any direction of the air, even counterflow and even parallel flow. You get almost the same capacity.
Excellent.
Yes, it depends of the application, and also, yes, as mentioned, the refrigerant. The properties of the refrigerant have a significant impact on this type of things, and the circuiting and everything. Thank you very much. So yes, it's increasing the velocity. What do I have here? This one is the one that I wanted to talk about you before. When I was talking about the liquid flowing through the wall of the piping. So for instance, some heat exchangers manufacturers have these special tubes that I don't know if you can see them, but they have like a grooved surface. I don't know how you call it in English.
Yeah, I know, grooved inside all the perimeter of the internal diameter of the pipe. So, and some are straight and some are on an angle. So that must mean something different.
Yes, this is very important. This is very important because it helps us to increase the velocity and also help us to increase the turbulence. So for instance, in a condenser, these ones are very common to be used because in a condenser, we have the inlet is gas and in the outlet is liquid, right? But in the middle, we have a mixture of that. So we want the waters to be flowing through all these like mini channels. So the gas is flowing through the inside, and not that by the gas flowing in the middle or in the inside of the piping help us to have also good velocities. And the same in the evaporators. However, these ones are not very common in the evaporators. And also by using this, we can also have an increase on the refrigerant pressure drop. So as mentioned, everything has an impact here. So it's not free. And also that we can do is also like increasing the fins per inch, but as mentioned before, if it's an evaporator, depends of the temperature, and if it's gas cooler, well, it depends of the regulations, for instance, like in the case of California, or it depends also of the air pressure drop when flowing through the coil. So now let's get what we are here, gas coolers.
Yep.
So we know that the primary function of a gas cooler or a condenser is to transfer heat from the refrigerant to the ambient or a cooling medium, depending on the heat exchanger, in order to condense or decrease the temperature. So for instance, if we have a refrigerant that doesn't have a phase change, well, we will decrease its temperature. If we have another type of refrigerant, well, we have a phase change. And for instance, the convection is the method by, sorry, I'm going to start again here. The heat transfer between the refrigerant and the cooling medium in the gas coolers or condensers occurs primarily through convection, because the hot refrigerant releases heat into the cooler medium as it flows through the coils or tubes of the gas cooler or condenser.
Yep.
And also we have a little bit of conduction, because within the walls of the heat exchanger tubes of our coils, the heat is transferred through conduction. But what is special about the gas coolers and the heat transfer in the gas coolers? Well, we know that our gas coolers are part of a transcritical system, right? But the gas coolers won't operate in transcritical operation the whole year. So it will be a condenser some months and a gas cooler some other months. And this is very important to consider, because the CO2 has some physical properties while working under the critical point, and has another physical properties while working as a transcritical fluid. Like for instance, the viscosity and the density are lower while working as a gas cooler. And this has a very big impact, because I have seen that, for instance, if I run a gas cooler, I will have, I don't know, let's say 10 psi of pressure drop. But while running it as a condenser, the pressure drop will be higher. And this is because of the properties. So this is very important to take into account, because it will have an impact on your entire system and also in your compressor. So for instance, some customers...
Yeah, so you're saying when you're in transcritical, it's the fluid is less dense? Is that what you said? Or than when in subcritical? That's right?
Yes.
Okay, perfect. And then the pressure drop is higher in subcritical condenser versus the transcritical gas cooler.
That's correct.
Okay.
And for instance, that's the reason why some of our customers tell us, please give me a gas cooler, but maximum pressure drop of 10 psi, or really maximum 15 psi, because they already know that when they are working under subcritical, the pressure drop will be higher, and the one, as mentioned before, the one that will pay for it will be the compressor, but it will be the customer's pocket, right? Yep. Because it means more electricity consumption.
Because when we're in transcritical, it's not a liquid now, and we're not condensing. We're a fluid. So it's a mixture. It's a percentage of gas and liquid inside this fluid, depending on how high you are. But when we go down into subcritical, we're actually condensing. So that turns into a liquid, and it's harder to move that liquid. Is that right? Am I explaining that right?
Yes.
Okay.
And yes, and in the gas cooler, we have sensible heat, because we are only decreasing the temperature.
That's right.
We won't have a phase change because we are in transcritical state.
Awesome. That makes sense.
Well, just to add a little commercial, about the adiabatic and the advantage of the adiabatic. This is a video. Give me a second. Okay. The advantage of the adiabatic is that it will help us to work in subcritical operation longer. And even though we have a higher pressure drop while working as a condenser, it's better to work as a condenser because our system is maintained in subcritical. So it will be working in lower temperatures and pressures, which will make our system more efficient.
Yeah, because now we have colder, we have less work on that high pressure valve. We got better heat transfer going into that flash tank vessel, that receiver. We got fluid. We could potentially have fluid coming out of the condenser now instead of going up into that transcritical mode where you're going to do more work in the system. So awesome.
Yes, well, this is all from my side, but I can see that we have some questions, so we can go with it. We still have time, right?
Yeah, no, I love it. We got a few questions here. The question about the formula is Q equal to U times A times LMTD.
Yes, that's the general one. But of course, if you want to calculate the overall heat transfer coefficient, there is another formula for that. And if you want to calculate the LMTD, if it's parallel flow, it's another formula. And if it's counterflow, it's another equation. But I just try to make it simple because sometimes when we see a lot of numbers, it's like more complicated to follow in my personal experience.
Yeah, no, that's exactly right. I like it simple. To calculate the convection coefficient for a gas cooler, how do we model the flow for liquid or for a vapor?
Well, for instance, well, I will say, thank God we don't have to do that because we already have a software that does that. But the software already considers. So let me start again. So when we want to do the calculation for a gas cooler, we use some criteria because the properties are different. And when we want to do a condenser, the criteria is different because the properties are different. So that's why, for instance, if I run the same unit as a gas cooler, I will have a capacity, but if I run it as a condenser, I will have a different capacity because the properties are different, even though the ambient temperature won't be the same because the transcritical state. But I mean, just to answer this question directly, there is like the special properties for the transcritical fluid. So it's not either liquid or vapor.
Yeah, that makes sense. Another one here. In transcritical, what is the value of density used for CO2 refrigerant? I think you can look that up. I wouldn't know that off the top of my head. You're definitely going to have to look that one up.
I don't know it by heart, but maybe we can Google it.
So one of the biggest things I've been learning over the last few years in sizing CO2 systems and designing transcritical systems is that the gas cooler plays a fundamental role in all the different heat exchangers in it. It's no different than any other refrigeration system. But with these ones here, when you go into transcritical, just like Tania said, you're above that 87 or 31 degrees Celsius, you're in that transcritical mode. That system is going to work a bit differently. Then the controls come into play. Like we talked with Will last week, and I highly recommend go watch that one, where that control system comes into play that Gutner designed, because now they're going to help that system stay in subcritical for more time of the year. And that's where that heat transfer comes into effect, and you get better heat transfer at that point versus, because you're getting both latent and sensible versus just sensible when you're in transcritical, correct?
Yes, I agree. That's correct.
I agree. I love that. Let's see, what else do we have here? Well, I think that's it for questions. Any final thoughts? Tania, any final thoughts? I really appreciate this. And I know we just touched the surface, but there's so much to learn about heat transfer. And I know you've learned a ton over the last few years, just growing your knowledge. Any final thoughts for any designers out there, any technicians when they're starting to learn about heat transfer, or maybe even designing systems with gas coolers or heat transfer devices?
I think that it will be to take into account that nothing is free. That I can give you more capacity, but maybe the size of the equipment will have to increase, which will be more expensive, or that I will have to use a bigger motor that will have a more power consumption, or that I will have to decrease the ambient temperature. Sorry, the evaporation temperature in the case of evaporators. So there is always an option, but it's not free.
Yeah, no, exactly. And this is I've just in a 12-week CO2 design course with some of my team, and when they were going through this, that was one of the things that we were doing the calculation of a whole CO2 system. So what's it cost the end user? And then they were diving into like this motor, this is exactly how long it's going to run, and they broke it all down. This is depending on where you're at in the world and how much time, this is how much this exact fan that's on top of the Guttner thing costs per year in this area. And I'm like, holy smokes, that's how you break it down. And then that's where I was like, because I used to not think, well, what's a fan motor? It's not a big deal. But it is a big deal when you have 16 of them and they're really big and you got a lot of airflow happening. So I thought that was really cool. Tania, I want to really thank you for taking the time to share some of this knowledge with us. I learned a ton, and I know a lot of people on here learned a ton. And I'm excited to have more conversation with you because I've learned a lot here, and I always do when we chat. And I'm excited to see you at another Refrigeration Mentor podcast, everyone. Thank you so much.